On March 1, 1954, the sky above Bikini Atoll in the Marshall Islands was torn apart by a light never before seen by human eyes. This was not the gentle break of dawn over the Pacific Ocean. This was the violent birth of a man-made sun, an event known to history as the Castle Bravo test. It was intended to be just one of a series of high-yield thermonuclear tests conducted by the United States, part of Operation Castle. However, Bravo would become infamous. It was a stark and terrifying demonstration of humanity's newfound power to harness the atom's core for destructive purposes. The test was meant to solidify America's lead in the Cold War arms race, but it did much more. It unleashed forces beyond the full comprehension of even its creators, shaking the world, both literally and politically. The event would forever change our understanding of nuclear weapons and their consequences. The purpose of Operation Castle was clear: to develop and test a dry-fuel thermonuclear weapon that was small enough to be delivered by an airplane. Previous fusion devices, like the Ivy Mike shot in 1952, were enormous, multi-story structures that use cryogenic liquid deuterium, making them impractical as deployable weapons. Castle Bravo was designed to prove a new, more efficient concept using a solid fuel, lithium deuteride. The scientists and engineers gathered on the control ship, USS Estes, located a safe 30 miles away, anticipated a significant explosion. Their calculations predicted a yield of around 6 megatons, an immense force equivalent to 6 million tons of TNT. Yet, as the fireball swelled with an unnatural and furious intensity, it became chillingly clear that their predictions were catastrophically wrong. The world was about to witness the single most powerful nuclear device ever detonated by the United States. The historical context of the Castle Bravo test is crucial to understanding its significance. The early 1950s represented the peak of Cold War paranoia. The Soviet Union had successfully tested its own atomic bomb in 1949 and was racing to develop its own hydrogen bomb. The United States felt an immense pressure to maintain its nuclear superiority. This urgency drove the rapid development of thermonuclear technology at facilities like Los Alamos National Laboratory. The scientists were pushing the boundaries of physics and engineering at a breathtaking pace. This race against time, however, came with immense risks. The science behind fusion reactions was still relatively new, and assumptions were made based on the best available data, but some of that data was incomplete or flawed, a fact that would have devastating and far-reaching consequences. The name Bravo was simply the letter B in the Joint Army-Navy phonetic alphabet used to designate the second test in the planned series. The device itself had a more casual, almost deceptive nickname: the Shrimp. This small name belied the immense power packed within its cylindrical casing. It was placed inside a simple structure called a shot cab on an artificial island built on the reef of Namu Island, part of the Bikini Atoll. From this humble platform, the Shrimp would unleash a destructive force 1,000 times greater than the bomb dropped on Hiroshima. The event marked a profound turning point, not just in military technology, but in humanity's relationship with the planet. It was a moment when the potential for global self-annihilation became terrifyingly tangible, etching itself into the collective consciousness of a generation. The Shrimp was a marvel of destructive engineering, representing the first practical application of the Teller-Ulam design for a dry-fuel thermonuclear weapon. Its architecture was divided into two main stages, each designed to perform a specific function in a rapid, sequential chain of events. The first stage, known as the primary, was essentially a sophisticated atomic bomb. Its purpose was to act as a trigger, creating the extreme conditions necessary to ignite the much larger secondary stage. This primary stage consisted of a plutonium core surrounded by conventional chemical explosives. When these explosives were detonated with perfect synchronicity, they created an inward shockwave, compressing the plutonium into a supercritical mass. This initiated a fission chain reaction, releasing an immense burst of energy and, most importantly, a flood of high-energy X-rays. The secondary stage was the heart of the hydrogen bomb. It was a large cylinder containing the fusion fuel, a solid compound called lithium deuteride. This was a significant innovation, as it was a dry fuel that was stable at room temperature, unlike the cryogenic liquid hydrogen used in earlier designs. Running down the center of this fusion fuel cylinder was a plutonium rod, often called the spark plug. The entire secondary assembly was encased in a thick shell made of uranium. Separating the primary and secondary stages was a crucial component made of a special foam-like material, typically polystyrene, housed within a radiation case. This interstage material was designed to be turned into superheated plasma by the X-rays from the primary explosion, a key step in the detonation sequence. The detonation process was a symphony of physics occurring in a fraction of a second. It began with the firing of the conventional explosives around the primary's plutonium core. The resulting fission explosion generated an incredible amount of energy, reaching temperatures hotter than the surface of the sun. This initial blast released a torrent of X-rays that traveled at the speed of light, outracing the physical shockwave of the explosion. These X-rays were channeled by the radiation case and instantly heated the polystyrene foam interstage, turning it into a dense, superheated plasma. This plasma then slammed inward onto the secondary stage with unimaginable force and heat, a process known as radiation implosion. This intense compression was the key to igniting the fusion reaction. The immense pressure and heat caused the plutonium spark plug at the center of the secondary to undergo fission, providing even more heat and neutrons. This was the final trigger. The lithium deuteride fuel was crushed to an incredible density and heated to stellar temperatures, forcing the lithium and deuterium nuclei to fuse together. This fusion reaction released an enormous amount of energy and a flood of high-energy neutrons. In a final, devastating step, these neutrons bombarded the uranium casing of the secondary, causing it to undergo rapid fission. This fission-fusion-fission sequence created a runaway reaction that amplified the bomb's explosive yield exponentially, resulting in the terrifyingly powerful blast of a thermonuclear weapon. The scientists at Los Alamos who designed the shrimp device predicted a yield of approximately 6 megatons. This calculation was based on a series of assumptions about how the materials inside the bomb would behave under the extreme conditions of a nuclear explosion. The fusion fuel itself, lithium deuteride, was composed of two isotopes of lithium, lithium-6 and lithium-7. The device was designed using lithium that was enriched to about 40% lithium-6. The scientific theory at the time held that only the lithium-6 isotope would participate in the fusion reaction. When bombarded by a neutron from the primary fission explosion, a lithium-6 atom would split into tritium and helium, with the tritium then fusing with the deuterium to release massive energy. The other component, lithium-7, which made up the remaining 60% of the fuel, was expected to be relatively inert. The physicists believed that it would not significantly contribute to the bomb's yield. This assumption was the single greatest error in the history of the American nuclear weapons program. It was a critical oversight that would have monumental consequences. The team believed that the lithium-7 might absorb a neutron, but they did not anticipate the chain of events that would follow. This fundamental miscalculation meant that the bomb they had placed on Bikini Atoll was not the 6-megaton device they had planned. It was, in reality, something far more powerful and far more dangerous than they could have imagined. The unexpected and terrifying reality of the Castle Bravo test was that the lithium-7 isotope was not inert at all. While it was true that lithium-7 required a much more energetic neutron to react, the conditions inside the exploding thermonuclear device were more extreme than anticipated. When a high-energy neutron from the initial fusion reaction struck a lithium-7 nucleus, it did not just absorb it. Instead, it caused the lithium-7 atom to decay, producing an alpha particle, a tritium nucleus, and another neutron. This was a completely unforeseen reaction. The newly created tritium nucleus was, of course, a prime fusion fuel, and the new neutron was free to cause further fission or fusion reactions. This unexpected reaction involving lithium-7 effectively tripled the amount of available fusion fuel inside the bomb. Instead of just the 40% of the fuel, lithium-6, participating in the reaction, nearly all of the lithium deuteride became fuel for the fusion fire. This created a runaway effect that the designers had not accounted for. More fuel meant a more intense and prolonged fusion burn, which in turn released a far greater number of high-energy neutrons. These neutrons then caused the bomb's natural uranium tamper to undergo massive fission, adding even more explosive energy to the final yield. The result was a catastrophic cascade of reactions that dwarfed the original predictions, turning a large explosion into a world-altering event. The final yield was not 6 megatons but a staggering 15 megatons, 2.5 times the expected power. At 6:45 a.m. on March 1, 1954, the shrimp device was detonated. In the first microsecond, an intensely bright fireball erupted, instantly vaporizing the shot cab, the artificial island it stood on, and tons of surrounding coral and water. For those watching from the control ship USS Estes, 30 miles away, the initial flash was blinding, even through protective goggles. The fireball rapidly swelled, glowing with an eerie palette of colors from deep red to brilliant white. Within a single second, it had expanded to a diameter of nearly 5 miles, creating a dome of superheated gas that was hotter than the core of the sun. The sheer scale of the energy release was beyond anything the observers had ever witnessed. The shock wave from the explosion traveled across the water, and when it struck the USS Estes, it felt like the ship had been rammed by a train. The vessel was rocked violently, throwing men and equipment across the decks. The heat from the blast was felt on the faces of the observers even from 30 miles away, a sudden searing wave of warmth like opening a giant furnace door. The fireball, no longer contained by the ground, began to rise, pulling with it millions of tons of pulverized coral, water, and debris. This material was irradiated and drawn up into the stem of what would become a monstrous mushroom cloud. The sound of the explosion arrived later, a deep, prolonged, thundering roar that seemed to shake the very foundations of the world. The mushroom cloud ascended with terrifying speed. Within 1 minute, its top had soared past 45,000 feet, higher than the cruising altitude of commercial airliners. It continued to climb, punching through the troposphere and into the stratosphere. In less than 10 minutes, the cloud reached its maximum height of about 130,000 feet, or nearly 25 miles high. At the same time, the cap of the mushroom cloud expanded horizontally, unfurling like a ghostly umbrella until it was over 62 miles wide. Observers on Kwajalein Atoll, some 250 miles away, reported seeing the unholy light of the fireball on the horizon. The explosion was so powerful that it carved a crater into the atoll's reef that was 6,500 feet in diameter and 250 feet deep, a permanent scar on the face of the Earth. The sheer visual spectacle of the explosion was both awesome and horrifying. The cloud itself was not the pure white often seen in photographs of smaller atomic tests. It was a dirty, pinkish-brown color, stained by the millions of tons of incinerated coral reef that had been sucked into its fiery vortex. This vaporized coral was now intensely radioactive, a key factor in the disaster that was about to unfold. The scale of the detonation shocked everyone involved, from the scientists who designed the bomb to the military personnel tasked with conducting the test. They had created a monster, and it had unleashed a power that was not only greater than they had expected, but also carried with it a deadly poison that would soon drift silently on the high-altitude winds. Okay, so, Section 5. The ghostly ash unforeseen radioactive fallout. The single most disastrous consequence of the Castle Bravo test was, the unprecedented amount of radioactive fallout it produced. Now, the term fallout refers to the residual radioactive material propelled into the upper atmosphere following a nuclear explosion. In this particular case, the fallout was primarily composed of pulverized and irradiated coral reef. Because, the bomb was detonated on the surface, it vaporized a massive amount of calcium carbonate from the coral, which then mixed with the fission products from the bomb itself. These particles, now intensely radioactive, were carried high into the stratosphere by the mushroom cloud. The sheer size of the explosion, far larger than anyone anticipated, meant that a much greater volume of material was irradiated and thrown to a much higher altitude. Complicating this dangerous situation was, another unforeseen factor: the weather. The test planners had checked the wind patterns before the detonation, and they believed that the winds would carry any fallout to the north, over a vast and empty stretch of the open ocean. However, their weather predictions were wrong. In the crucial hours after the explosion, the high-altitude winds shifted unexpectedly, blowing strongly to the east. This change in wind direction would prove to be, catastrophic. Instead of dispersing harmlessly over the ocean, the massive 60-mile-wide cloud of radioactive particles began to drift directly over a series of inhabited atolls and into a region of the Pacific used by international fishing fleets. The fallout began to descend from the sky a few hours after the explosion. It was not a fine, invisible dust. Survivors described it as a white, gritty, snow-like powder. On the atolls of Rongelap and Udarik, which lay directly in the fallout path. Children were initially fascinated by the strange snow. They played in it, not understanding the invisible poison it contained. The powder accumulated on the ground, on the roofs of homes, and in the cisterns used for collecting drinking water. It was a silent and deadly blanket, covering everything with a fine layer of radioactive isotopes like strontium-90, cesium-137, and iodine-131. These substances emit dangerous radiation that can penetrate the human body, causing severe cellular damage. The area contaminated by the Bravo fallout was immense, covering more than 7,000 square miles of the Pacific Ocean. The plume of lethal radiation was not narrow or predictable. It spread out in unpredictable patterns, creating hotspots of intense contamination hundreds of miles from the test site. Within hours of the test, the American task force realized the gravity of their miscalculation. Radiation monitoring instruments began to show dangerously high readings far from the expected danger zone. A frantic and delayed effort to evacuate the affected populations began, but for many, it was already too late. They had been exposed for hours, and in some cases days, to levels of radiation that would cause immediate sickness and long-term health problems that would haunt them for the rest of their lives. Drifting on the Pacific Ocean about 82 miles east of Bikini Atoll, there was a Japanese fishing boat called the Daigo Fukuryu Maru, or the Lucky Dragon No. 5. Its 23 crew members were out there, hauling in their lines of tuna, when suddenly, they saw an unbelievably bright flash in the western sky. They were startled, honestly confused, and later described the light as the sun rising in the west. Just a few minutes after that, they heard this distant, thunderous boom from the explosion. The crew, well, they had no idea a nuclear test was even happening nearby. They were just fishermen, doing their work in what they believed were safe international waters, far outside the official danger zone that the American government had declared. But their actual location placed them right in the path of the radioactive cloud drifting eastward. About 2 hours after the explosion, a fine white gritty ash started to fall from the sky, covering the deck of the Lucky Dragon. The fishermen were curious, but not really alarmed at first. Some of them even tasted the gritty stuff, saying it was pretty bland. They picked it up in their hands, watching it fall like some strange, tropical snow. They just kept working, not realizing that every single particle of that white ash was intensely radioactive. Over the next several hours, the crew members started to get sick. They had headaches, nausea, and pain, and burns on their skin wherever the fallout had landed. They'd been exposed to a massive dose of radiation, an event that would soon become an international incident, and really, a symbol of the human cost of the nuclear age. By the time the Lucky Dragon got back to its home port of Yaizu in Japan, 2 weeks later, the crew's condition had gotten much worse. Their skin was blackened and burned, their hair was falling out, and they were suffering from severe radiation sickness. The discovery of the irradiated ship and its sick crew caused a huge public outcry in Japan, a country that had already experienced the horror of nuclear weapons at Hiroshima and Nagasaki. This incident sparked a massive anti-nuclear movement and created a significant diplomatic crisis between Japan and the United States. The contaminated tuna brought back by the boat led to widespread panic about the safety of the nation's food supply, and tons of fish had to be destroyed. The story of the Lucky Dragon ended in tragedy. Despite receiving medical treatment, the ship's chief radio operator, Aikichi Kuboyama, died 6 months later on September 23, 1954. His death is widely regarded as the first fatality from a hydrogen bomb. His last words were, reportedly, "I pray that I am the last victim of an atomic or hydrogen bomb." The other 22 crew members suffered from chronic health problems for the rest of their lives, including liver damage, blood disorders, and a higher risk of cancer. The fate of the Lucky Dragon crew brought the hidden dangers of radioactive fallout to the world's attention, turning it from an abstract scientific concept into a terrifying and very real human tragedy. For the people of the Marshall Islands, the Castle Bravo test wasn't just some distant historical event, it was the start of a multi-generational tragedy. The inhabited atolls of Rongelap, Ilanginai, and Utarik were directly in the path of the radioactive plume. On Rongelap, which is about 125 miles east of Bikini, residents watched as a strange white ash fell for hours. The children, not knowing any better, played in the snow, rubbing it on their skin. The powder contaminated their homes, their food, and even their drinking water. Within hours, the islanders began to suffer the acute effects of radiation poisoning, severe skin burns, vomiting, and hair loss. And yet, it took more than 2 full days for the US military to arrive and evacuate the 82 residents of Rongelap. This delay turned out to be devastating. The evacuation was only the beginning of a long and painful journey for the Marshallese people. They were taken to Kwajalein Atoll for medical observation, but by then, the damage was already done. They had absorbed life-threatening doses of radiation. The people of Uttarik, which was further east, got a lower but still significant dose of fallout. They were evacuated 3 days after the test. For years, these displaced communities were moved from island to island, unable to return to their contaminated homes. The United States government told them it was safe to return to Rongelap in 1957, but that turned out to be a terrible mistake. The island was still dangerously contaminated, especially with cesium-137, which had been absorbed by the plants that made up their traditional diet. The long-term health consequences for the exposed populations have been, honestly, catastrophic. In the years after the test, the people of Rongelap and Uttarik saw alarmingly high rates of thyroid disorders, including cancerous tumors. Because radioactive iodine concentrates in the thyroid gland, many, especially those who were children at the time, had to have their thyroids surgically removed. There was also a tragic increase in stillbirths, miscarriages, and children born with severe birth defects, which the Marshallese called jellyfish babies. The psychological trauma of all this, combined with the loss of their ancestral lands and traditional way of life, has left deep and lasting scars on the community. Even today, many of the atolls, including the once paradisiacal Bikini, are still uninhabitable. The radioactive isotopes left by Castle Bravo and other tests have very long half-lives, meaning they'll contaminate the soil and water for thousands of years. The people of Bikini remain exiles, scattered across the Marshall Islands and the world, unable to return to the land of their ancestors. The United States has provided some financial compensation and medical care, but, honestly, many Marshallese feel it's nowhere near enough for the scale of the suffering they've endured. Their story stands as a powerful and heartbreaking reminder that the consequences of nuclear testing aren't temporary. They are, in fact, a permanent poisoning of land, culture, and entire generations of people. In the aftermath of the Castle Bravo test, the US government started a top-secret medical study with a rather chillingly bureaucratic name, Project 4.1. The official title was Study of Response of Human Beings Exposed to Significant Beta and Gamma Radiation Due to Fallout from High-Yield Weapons. The subjects of this study were the unfortunate residents of Rongelap and Uttarik, the Marshallese people who'd been accidentally irradiated by the fallout. While the US government publicly said it was providing humanitarian medical aid, the real purpose of Project 4.1 was to conduct a long-term study on the effects of radiation exposure on a human population. The Marshallese people became, in effect, human subjects in a very real and horrifying experiment. For decades, American medical teams from the Brookhaven National Laboratory visited the islands every year to conduct exams. They drew blood, collected urine samples, checked for tumors, and documented the long list of health problems affecting the population. The Marshallese people weren't told that they were part of a research study. They believed they were just receiving medical care from the nation responsible for their suffering. This lack of informed consent is honestly one of the most troubling aspects of the whole Castle Bravo affair. The data collected was highly classified and used by the US military and the Atomic Energy Commission to better understand the biological effects of nuclear fallout, knowledge that would be, well, valuable in the event of a nuclear war. The findings of Project 4.1 documented a grim catalog of human suffering. The study carefully recorded high rates of thyroid cancer, especially among children who were exposed. It noted growth stunting in boys who were young at the time. It tracked miscarriages and birth defects that plagued the community for years. While this information was scientifically valuable, it was gathered in a context that many critics, and the Marshallese themselves, have described as exploitative. They were treated less as patients deserving the best possible care and more as a unique data set, a living laboratory for studying the consequences of a nuclear disaster. The existence and nature of Project 4.1 were kept secret for many years. When the details finally came out, they sparked outrage and accusations that the United States had treated the Marshallese people as guinea pigs. U.S. officials have always denied these accusations, saying the main goal was medical care and that the research was just a secondary benefit. But declassified documents and the testimony of the Marshallese people tell a much more complicated and disturbing story. The legacy of Project 4.1 has created a deep and lasting mistrust between the Marshallese and the U.S. government, a wound that's never really healed and remains a dark chapter in the history of medical ethics and the Cold War. The Castle Bravo test was honestly a watershed moment that sent shockwaves through the international community. The sheer, uncontrolled power of the explosion and the horrifying story of the Lucky Dragon No. 5 brought the dangers of thermonuclear weapons out of the realm of military secrets and right into the public consciousness. Before Bravo, a lot of people saw nuclear testing as some remote and necessary part of national security. But after Bravo, the world had to face the reality of radioactive fallout, an invisible poison that could travel for hundreds of miles on the wind, contaminating huge areas and harming anyone, anywhere, in its path. This new awareness fueled a growing global movement to end atmospheric nuclear testing. The diplomatic fallout was immediate. Japan's outrage over the irradiation of its fishermen put a real strain on its relationship with the United States. Around the world, a new wave of anti-nuclear activism took off, with prominent scientists and thinkers like Albert Einstein and Bertrand Russell speaking out against the existential threat posed by the hydrogen bomb. The Bravo test made it terrifyingly clear that a full-scale nuclear war wouldn't just destroy cities, it could make large parts of the planet uninhabitable for generations. This realization gave a strong push to arms control negotiations, as both superpowers started to understand that the weapons they were building could actually threaten the survival of humanity itself. One of the most significant long-term consequences of the Castle Bravo incident was the signing of the Partial Test Ban Treaty in 1963. This landmark treaty, signed by the United States, the Soviet Union, and the United Kingdom, banned all nuclear weapon tests in the atmosphere, in outer space, and underwater. While it still allowed underground testing, it was a crucial first step in slowing the nuclear arms race, and, maybe most importantly, it ended the practice of spewing massive amounts of radioactive fallout into the atmosphere. The global contamination, from Bravo and other tests, had become a measurable and frightening reality, with radioactive isotopes like strontium-90 being found in the teeth of children all around the world. The treaty was, without a doubt, a direct response to this global health crisis. Looking back from today, on October 28, 2025, the echoes of Castle Bravo still resonate. It stands as a stark lesson in scientific hubris, a cautionary tale about the unforeseen consequences of pushing technology to its destructive limits. The event highlights the profound ethical responsibilities that come with scientific power. The poisoned atolls and the lingering health problems of the Marshallese people are a permanent reminder of the human cost of the Cold War. Castle Bravo was more than just a bomb test. It was a moment when humanity looked into the abyss of its own creation and, for a brief, terrifying instant, saw the potential for its own end. The lessons learned from that fiery dawn in the Pacific remain as critical today as they were over 70 years ago.